1787, Carl Friedrich Gauss is 10 years old. His teacher gives the kids in the one-room schoolhouse in Germany a bit of busy work, says add up all the numbers from 1 to 100. Carl almost instantly knows the answer is 5,050. He did it through a trick that most of my students have heard about and that anybody can look up. But what he was really doing was inventing a formula for adding up a great deal of numbers, adding up consecutive integers. The formula he was inventing as a 10-year-old, well, it's a 10-year-old little show-off, was this. The sum of some number of integers added together is the number of integers divided by 2 multiplied by the quantity first integer plus the last integer. Now for Carl, this was the numbers 1 to 100. So he was being asked to add 100 numbers. And the first number was 1, and the last number was 100. So we do a little algebra now using this shortcut he basically invented, and we get that it's 50 times 101. 50 times 100 is 5,000. 50 times 1 is 50. The answer is 5,050. He did it that fast. He was a smart little guy, 10 years old. And he went on to invent major areas of, well, number theory. So he came up with this formula and it worked. How do you know this will always work? How do you know this will work out to infinity? Why would this formula keep working forever? Another question is why wouldn't it? But you know, in math, nothing is true unless it's always true. So we have to prove that this formula for adding integers always works. This sum formula for adding them. We're going to use something called mathematical induction. Okay? Here's what mathematical induction says. It's a proof that tells you if something keeps working. I like to compare it to climbing a ladder. All right, so mathematical induction is, can you climb this ladder forever? So first what you have to do is find the first rung of your ladder. It's the first step of mathematical induction. Does the first rung hold weight? Will your ladder work just right from the get-go? So step 1 for a proof by induction is verify your conjecture, that's your idea, is valid for the first possible case. All right, this is a little bit confusing. The first possible case for adding up all the numbers from 1 to 100 is 1. So our first question seems a little odd, but if we use this formula to add up all the numbers from 1 to 1, will we get the right answer? Well, what do you get if you are told to add up all the numbers starting at 1 and also stopping at 1? All you've pretty much done is said the number 1 out loud. So it's a weird case, but you've got to test it. You've got to see if the first rung on your ladder works. So the way this plays out with this formula is, what is the sum of one number out of a list of one number where the first number is 1 and the last number is also 1? This formula is literally a way to say, add up the integers from 1 to 1. This is an answer we know. We better get 1. So the sum of the number 1 added to nothing is 1/2 times 2 is equal to 1. Silly step, it may seem, but it's vital. You have to be able to check this off, okay? You have to know that your formula works in the simplest possible case. This is the simplest possible case, okay? That's the first step in math proofs by mathematical induction. Second step. The second step is, does it work for all the other numbers? Now, someone out there is going to listen to this and say, Okay, so now we just keep adding up numbers until we get to infinity, and then we say, it works. No, we can't do that. It's not even possible. The second step is to prove that it works between any other two numbers. Do the rungs on your ladder work all the time? Can you get from one rung to another? Is it within reach? And to do that, we have to test this for the distance between any two numbers in our pattern, and we have to do it without plugging in specific numbers. So how do we do that? Okay, let's take another look at what this formula is. This is the formula for the sum of consecutive integers. It's actually useful in some other ways, but this is the only thing we care about right now. Okay? So I'm going to set up a little idea for you here. Let's say we were adding up the first 10 integers. The sum of the first 10 integers would be 10 over 2, because it's 10 integers long, the list, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The first number would be 1, the last number would be 10. Okay? Now the sum of the first 11 integers could be written two different ways. It could be written as the sum of 11 over 2, since there's 11 numbers in our list, times 1 plus 11. That would work. It could also be written as the sum of the first 10 integers plus the number 11. Does that idea make sense? If you have a formula for the sum of the first 10 numbers, 10 counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, your formula should work for the sum of the first 11 numbers as well, or you could use this formula to add up the first 10 numbers and then just add 11 to that. You can see if it works between 10 and 11. Okay, but I'm not really interested in that specific a case. I don't want to test this between 10 and 11, between 20 and 21, between 30 and 31. That won't tell me that it always works. I want to test this idea in general. In other words, I want to know if this formula works between any two consecutive numbers I can imagine. I want to know if the sum of the n plus 1 number on my list, whatever number that is equal to the sum of the nth number on my list plus the next number. I want to know if the sum of the 11th number is equal to the sum of the first 10 numbers plus 11. I want to know if the sum of the first 100 numbers is equal to the sum of these first 99 numbers plus 100. But I want to do this in general. So how do we do that in general? Well, we prove this with algebra. We don't put in any numbers. Here's my general sum formula up here. Here's what I want to prove for my second step. Okay? A lot of textbooks substitute n's and k's for now. It doesn't change the math, but that's okay. N is the total number in your list. They want to use k as a counter. I'll stick with n for now because it's a little simpler. So what they're saying is, okay, if I want to know the sum of the n plus 1th term, what I should do is put n plus 1 into my formula. So what this means is n plus 1, okay, over 2 equals, now we're doing counting numbers. We're talking about the sum of consecutive integers. We're testing a little Carl's idea. So a sub 1 in this case is still 1. And we're counting until we get to n plus 1, whatever that is. If n is 100, this should get me the sum of the first 101 integers. If n is 20, this should get me the sum of the first 20 integers. Now, if this is going to work, I'm going to compare that to what I get if I just took the sum of n integers. That's just my original formula. And to that, I add the nth plus 1 number. So what I'm doing is I'm seeing if the sum of my first, say, 11 numbers is the same thing as if I were to add up the first 10 numbers and then add the 11th number to that. Should work. Hopefully it'll work. But if I do it with ends, if I don't plug in 10 and 11, if I don't plug in 20 and 21, if I don't plug in 100 and 101, if I can prove it just with algebra, leaving these as variables essentially, then I'll know it works forever. It'll work for any numbers. If this side of the equation can be made to be true, the same thing as this side of the equation, I'll know I have a pattern that works for any numbers I can imagine. I will actually have proven that Carl's formula works all the way up to infinity, because I'll have gotten a true statement with no numbers plugged in. So let's do some algebra. Give myself a little more room to do some algebra. All right, let's see now. This is not going to be very clear if I write it that way. This is n plus 1 over 2. Make this a little bit more neat. 1 plus n plus 1, and that's n plus 2. Here, I have n times n plus 1 over 2 plus, let's make a common denominator, 2 times n plus 1 over 2. Are these starting to look like the same thing yet? I'm not entirely sure. So over here I'm going to get n plus 1 times n plus 2 over 2, whereas over here I am going to get n times n plus 1, same denominator already, plus 2n plus 2 over 2. I've combined my fractions, I've distributed a little bit. Let's FOIL over here. I get n squared plus 3n plus 2 over 2 on this side, and on this side I get n squared plus n plus 2n plus 2 all over 2. Well, this is starting to look pretty similar. In fact, 3n is the same as n plus 2n. Everything else is the same. I can put a check mark, and I can now say that this formula, the sum of n number of consecutive integers, will always be equal to this formula for any number of consecutive integers I can imagine. Why? Because I set up the original formula plus the next term and proved it was always equal to the original formula if I put n plus 1 in as the term. The original formula plus the next term is equal to the original formula with n plus 1 put in. I did the algebra. I got the same thing on both sides. Must be true. Has to work for any numbers you can imagine. If you plug in 5 and 4, you'll get a true statement. If you plug in 1001 and 1000, you'll get a true statement. This formula always works. Let's try for something a little more difficult. So here's a slightly more difficult example. Not much different from the last one. What we're going to do is we're going to prove that this series, has this summation formula. In other words, if you want to know what happens when you add up all the numbers of this series, or any particular number of these series, this will be a shortcut rather than actually going through the trouble to add 3 plus 5 plus 7 plus 9, etc. Okay? So, let's take a look at what we're actually talking about with this sequence here. Well, first thing, we have to do step 1. Does this formula actually work for the first possible case? In other words, to put it in terms of sequences and series, when n is 1, do we get a sub 1 equal to 3? See, according to this sequence, The first term is 3. So if I put 1 into my summation formula, I should get 3. All right, so let's try it. Step 1 of our induction proof. When n equals 1, the sum of the first term is 1 times 1 plus 2, which equals 3. We did actually get the first term with our summation formula. Okay, that's it. That's all there is to the first step. Does plugging in 1 for n into your summation formula actually get you the first term of your series? Yes, it does. Awesome. We can go on to the next step now. And the next step says that, can we prove that this works between any two numbers we can imagine? All right, and the general form of that, well, let's see what we're looking at here. First off, what they're telling us is a little bit interesting. They're telling us, believe it or not, that this is your implicit formula. That may not be obvious. What they're saying is a sub n can always be found by 2n plus 1. And they're telling you, whether you notice this or not, that what's on the other side of the equal sign is your summation formula. They're saying the sum of n terms is n times n plus 2. If you want to know the sum of the first 100 terms, put 100 in for n. So with that in mind, what we're trying to prove for this particular series is that if you take the sum of the first any number of terms and then you add the next term, you should get the same thing as if you use the sum formula for n plus 1 terms. If we plugged 4 into this formula, we should get the 4th term. Okay? If we plugged 4 into this formula, we should get the sum of the first 4 terms. If we plugged 4 into this formula and got the sum of the first 4 terms, and let's say we plugged 5 into this formula and got the 5th term, that should be the same thing as if we added them together. Instead of that, this should be the same thing as if we just plugged 5 into our sum formula. The sum of the first 4 terms plus the 5th term should equal the sum of the first 5 terms. The sum of the first 100th term plus the 101st term should equal the sum of the first 101 terms. But we're not going to prove it with specific numbers. We're going to do this in a general algebra sense. So what that looks like for this formula is, and a lot of textbooks switch to k at this point. We're actually a step sooner, so I'll go ahead and do that. That looks like k times k plus 2, that's our sum formula, plus 2 times k plus 1, that's our implicit formula for the next term. And this should be the same thing as if you plugged k plus 1 into your sum formula everywhere we see an n. So if I've done this correctly, here is, this will be the summation formula. This is the summation formula for k terms, whatever number that is. Then we have the implicit formula for the next number in our series, and that should equal the summation formula for that next number in our sequence, or series, excuse me. If this works algebraically, I have proven that this formula works forever. So let's do the algebra. Don't need the highlighting anymore. So now we get k squared plus 2k plus 2k plus 2 plus 1 on this side. K squared plus 2k plus 2k plus 2 plus 1. And this is equal to k plus 1 times k plus 3 on this side. Combine some like terms over here, and I'm going to get k squared plus 4k plus 3. Foil on my right side of the equation, and I'm going to get k squared plus 4k plus 3. Check. By plugging in k into our summary formula, and then k plus 1 into both our implicit formula, and then on the other side of the equal sign, plugging k plus 1 into our summation formula, I got an algebraic expression which, if proven true, absolutely proves that this formula works out to infinity. Done. It's proven. Show you another way this is useful. It's another set of techniques you can use with mathematical induction. Now, mathematical induction can be used in a lot of ways. I'm only going to cover two of the ways it's used. One is proving summation formulas, and the other is divisibility rules. We are now going to prove that 4n minus 1 as an expression is divisible by 3 as long as n is a positive integer. Okay, sounds a little weird. What it means is if you take 4 and raise it to any integer power, subtract 1 from that, you'll always get something divisible by 3. First step. Well, let's test it, okay? First we do our anchor step, our proof for 1. Does this work for the very first case? Can we find that first rung on our ladder? 4 raised to the first power, putting 4 in for n, minus 1 is 3. Check, because 3 is divisible by 3. Seems like a little bit of a silly step, but you gotta make sure that your idea works the very first time you try to use it, okay? Second step gets a little bit crazier. I want to improve this now. 2. First, I'm going to restate this idea. The idea that 4 raised to the nth power minus 1 is always divisible by 3 can be rewritten as 4 to the n minus 1 equals 3 times r, where r also equals an integer. If 4 raised to the n power minus 1 is going to be divisible by 3, then it's going to be equal to 3 times some whole number. That's what divisible by 3 kind of means. Okay, it's another way to say the same idea. So if this is true, all right, then our idea is true. We're going to go ahead and, well, we know this is true for 1. I'll go ahead and tell you, we can check it for 2. 4 squared minus 1, 16 minus 1, 15. 15 is 3 times 5, boom. Works for 2. I could go on 3, 4, 5, 6. We know this at least works sometimes. So let's pick one of those times that we know it works. Let's pretend we're starting at a time that we know it works. It could be when n equals 1, 2, or 3. And let's see if we can prove in general it works if we just add 1 to this exponent. If we get 1 more in this exponent. All right, well, how do we do that? Well, the only way to change what's in an exponent is to multiply by the base again. This is 4 to the first power. If I multiply 4 to the first power times 4, I'm supposed to add these exponents. This will become n plus 1. So you have to find out if 4 to the n plus 1 is also, minus 1 is also divisible by 3. That's the tricky part. To do that, I've got to change this to 4 to the n plus 1. Only way I know how to do that is to multiply by 4. But if I multiply by 4, I have to multiply everything by 4. That means I have to multiply the other side of my equation by 4. Okay, so let's see how this works. 4 times 4 to the n. Well, that gets me 4 to the n plus 1. Good, that's what I wanted. Minus 1, though, now becomes minus 4. And over here, I have 12r. Okay, the thing is, I'm trying to prove that if I start with 4 to the n minus 1 is divisible by 3, 4 to the n plus 1 also minus 1 is divisible by 3. I can't change the second number. This would be a new formula. This has to be minus 1. I need 4 to the n plus 1 minus 1. Okay, well, how do I do that? I can subtract 3 from both sides. See where that leaves me. Well, algebraically, that leaves me with 4 to the n plus 1 minus 1 equals 12r minus 3. Okay, let's recap what we've done. We start with the idea that 4 raised to the nth power minus 1 is divisible by 3. That's what this part means. Now, we've isolated 4 to the n plus 1 minus 1. We've isolated the next element in our sequence, okay? And we're asking ourselves, we did it just by manipulating the algebra, okay? We didn't bring in anything new to do it. And we're asking ourselves, is this other side still divisible by 3? Well, let's take a look at that other side. 12r minus 3, I can factor a 3 out of both terms, and that gives me 4r minus 1. Okay, now remember our original condition. R has to be an integer. If r is an integer, and we multiply it by 4, we still have an integer. If we subtract 1 from that integer, we still have an integer in here. And 3 times any integer will produce a number divisible by 3, so check. We started with the idea that 4 raised to the nth power minus 1 would be a number divisible by 3, and we proved, just by multiplying both sides by 4, then subtracting 3, that the next element in our sequence, 4 to the n plus 1 minus 1, is also something that will be divisible by 3 for any number you can imagine. Done. We've proven it. Until you get used to the idea of mathematical induction, it can be hard to know when to stop. You get to a final statement and you're like, okay, what have I just proven? It takes practice, and that's why we're only going to focus on 2 types of mathematical induction: summation formulas and divisibility rules. I'm going to show you one more example and one more trick you can use. It's not one you'd be likely to figure out on your own. It's a little bit of a cheat, but it's good to know. Okay, here's a more complicated version of a divisibility problem. Prove that 6 raised to the nth power minus 2 raised to the nth power will always be divisible by 4 for any integer value of n you can imagine. Okay, seems reasonable enough. So we start with step 1. Our anchor step is 6 to the first power minus 2 to the first power. Well, that's just equal to 6 minus 2, that's equal to 4. Yes, we did get a number divisible by 4. The first rung of our ladder holds. Now we have to set up a pattern between any future rung on this ladder, any higher rung on this ladder we can imagine, and the next consecutive one. So let's set that up. Step 2 is we start with the idea that 6 raised to the nth power minus 2 raised to the nth power, in order to be divisible by 4, it must be able to be rewritten as 4 multiplied by some other integer r, some other whole number. This has to be true. And now our goal, what we're trying to achieve, is that 6 raised to the n plus 1th minus 2 raised to the n plus 1th power, if that's a word, will also be equal to something divisible by 4. So to do that, we need an algebraic way to get both of these powers increased by 1. Okay, had a little glitch there in the recording equipment. So let's see where we left off. We are looking at a mathematical induction proof. We're trying to prove that 6 raised to the nth minus 2 raised to the nth as an expression will always get you something divisible by 4. So we test it for n equals 1, and then we set up an expression that says in algebra what this sentence says in English, which is that 6 raised to the nth power minus 2 raised to the nth power is equal to 4 multiplied by something we're going to call r, where r must equal an integer. And our goal is to demonstrate that 6 raised to the n plus 1th power minus 2 raised to the n plus 1th power, which is an expression for the next term in this sequence. We want to know that 6 raised to the n plus 1 minus 2 raised to the n plus 1 will also get us something divisible by 4. Okay, with that in mind, I'm going to do some steps that may seem a little counterintuitive. They may seem a little surprising, but they will work. This is just a trick for how to solve mathematical induction proofs that look almost exactly like this. It's not a very general trick. It really won't work for much else, I've got to tell you, but it's worth learning. So, first thing I'm going to do is add 2 raised to the nth power to both sides. This will help me in a minute, because what I'm going to do next is multiply both sides of this equation by the number 6. But I'm going to do it in kind of an interesting way. This side, I'm going to multiply by 6. Why am I multiplying by 6? Well, I know that in my answer I need 6 raised to the n plus 1. Multiplying by 6 will get me that. But I also need 2 raised to the n plus 1. How does multiplying by 6 help me with that? Well, I'm going to put parentheses around this side, and I'm going to multiply by 2 plus 4. I'm allowed to multiply one side of my equation by 6 and the other side by 2 plus 4 because, well, 2 plus 4 is equal to 6. Let's see what I get. On the left side of my equation, I get 6 to the n plus 1. Good. I was looking for something with 6 to the n plus 1 in it. On the far side of my equation, the right side, I have to FOIL. First gives me 2 to the n plus 1. Good. I'm also looking for one of those. Then I get plus 4 times 2 to the n. Then I get plus 8r. And then lastly, I get plus 16r. Okay, why did I do this? Well, now I'm going to bring this 2 to the n plus 1 back over to the other side by subtracting 2 raised to the n plus 1 from both sides. And this leaves me with 4 times 2 to the nth plus 24 times r. Okay, so why do it this way? Well, remember our goal. I'm trying to get a separate expression, one side of my equation equal to 6 raised to the n plus 1 power minus 2 raised to the n plus 1 power. I've done that. And now, what I have to demonstrate somehow is that the left side of the same equation is divisible by 4. Well, I have a 4 that I can factor out of both terms. I can take a 4 out of the term 4 times 2 to the nth, and I can take a 4 out of 24r, and it leaves me with 6r. Now remember, n and r both have to be integers. If I raise 2 to any integer power, I get an integer. If I raise r to any integer power and I multiply it by 6, I get an integer. Add 2 integers together, it's still an integer, and any integer multiplied by 4 is, by definition, also divisible by 4. So I've just demonstrated that as long as the original expression is true, the next expression in a row is true. And since I know the original expression is true for 1, it must also be true for 2. Well, now I know it's true for 2. If it's true for 2, it must also be true when n is 3. When n is 5, it's also going to be true when n is 6. Mathematical induction lets us prove that a pattern will hold between any two rungs of a ladder. It lets you prove that the pattern holds as you keep adding to any sequence or series that you know to initially be true. And I've only shown you 2 tricks for mathematical induction, but they're usually the only ones you study in a precalculus course: summation formulas and divisibility rules. We may look at 1 or 2 others, but these are the biggies. And that is mathematical induction and how it works.